Okay, good afternoon, everyone. We'll start our final session for the day. And our keynote is Professor Nicholas Spirazauli. Sorry about the pronunciation, my apologies. Professor Nicholas has received his PhD in 1992 from the University of Nice, Sophia Antipolis, for the study of polymeric materials and materials for energy storage. He is currently a professor of exceptional class at the University Côte d'Azur, France. And his research interests involve the development of kinetic methods for studying polymerization mechanisms, amongst many others. So welcome, Professor. His title today is Thermal and Mechanical Properties of Furan-based Thermoplastics and Bio-based Epoxy Thermosets. Over to you.
Thank you for your kind introduction. Good afternoon, everyone, and I would like to thank the organizer of this conference. Very nice place for the invitation and give me the opportunity to present you my results. So thank you, Elisabetta. Thank you, Maria Laura, for invitation. So today I will present you a slightly different subject. And the idea is to show you some information that we can get from thermoanalytical techniques. And I hope if you're interested, we can imagine to make some collaborations. So I am working in Nice, in Faculty of Science, so a beautiful place, which is called Parc Valrose. And I invited you if you want to visit us. So just briefly, the theoretical background. I don't want to go too much into detail in this lecture. So the idea is not that we understand everything, but just to follow and see what we can do with this method and maybe think about the opportunity to apply to your systems, maybe if you're interested. So for kinetic analysis, we use what we call the basic rate equation. We have the reaction rate. You recognize pre-exponential factor, activation energy, and so on. One important parameter for kinetic analysis is what we call the extent of conversion here. And it can be easily obtained by DSC measurement because we just divided the heat at one time by the total heat release. But I also have developed some special methods to apply this method to rheology, DMA. For thermogrammetry, it was already existing. But with rheology, dynamical mechanical analysis, as I will show you. To summarize, for kinetic analysis, we have two kinds of methods. The first one is the model fitting or model-based. Nowadays, we do not recommend the single-step model fitting. I will not go into detail, but I am in the ICTAC Kinetic Committee, so we publish some recommendation not to use simple method that were used in the past. But at that time, the computers were limited, which is not the case now. So we have the model-based. The model-free kinetics, maybe you know a little about this approach, which is completely different. And I will show you today that now we also try to show that mixing the two approaches can be very interesting. So briefly, for model-free kinetics, I am using what we call isoconversional methods. So with isoconversional methods, we do not treat only one curve, one heating rate. So we use several heating rates or cooling rates. Here you have the integration, but we can work with differential data. But if you have integrated data, you have the extent of conversion. And what you look for is you select one constant value of this extent of conversion, and you look to the temperature or to the time according to the method you use. So each time you are working at a constant value of the extent of conversion, and this is the reason why you don't need to introduce the reaction mechanism in the equation, and that's why it's a good complementarity with the model-based. So then you repeat this, so always working for extent of conversion constant at a different heating rate, and you repeat the computation for all the value of extent of conversion. And we can show, but I don't want to go into detail with the equation, we can show that in that case, we can determine what we call the effective activation energy, the apparent activation energy. And the interest is that it is determined without any hypothesis on the reaction model. The problem with the model base, maybe if you already have tried, is that it is very difficult to select the right mechanism. You have many possibilities. You have many functions that you can select, and it's very difficult. So you always obtain a good fit of the data. So for model fitting, it's okay. But if you want to get some information with the physical meaning on the parameters, it's much more difficult. So that's why some information that we can obtain with the model-free kinetics is very interesting, and then we can combine the two approaches to go further. So with isoconversional method, if you have a single-step process, you will obtain a constant value of the activation energy, which corresponds to what we all know, activation energy, energy barrier, it is a constant. Now, single-step processes are not really interesting because it's not very frequent. So what about multi-step process? In the case of multi-step process, we will obtain a variation of this apparent activation energy. And now the difficulty is to interpret this variation. The first information that we have is that now we know that it is a multi-step process. So first, we must not use single-step method. This is first information. And then what we observe is that generally, this variation in activation energy corresponds to change in the overall reaction rate. It can be crystallization, it can be polymerization. And so we can try to extract some information on the mechanism. So first example I'll show you concern thermoplastic polymer. So what we can do on thermoplastic polymer. We can try to get a new insight in crystallization kinetics and mechanism. We can also, I will show you, make a prediction of the temperature at maximum grow rate, and we can make simulation of the crystallization rate curve. What about polymer crystallization kinetics? You probably all know the Avrami theory. And the second Avrami theory was developed for primary crystallization. And another theory is the Hofmann-Norrissen theory that I will show you, I use in my study that correspond to secondary crystallization. So why I do not use the Avrami equation? Because I have to recall that it was developed to describe isothermal crystallization. And if you look to this equation, you will see that you have only one rate constant. So it is a single-step equation. So if you have a multi-step process, this method must not be used. You have to remind also that the Avrami model was developed for crystallization of metals and does not account for specificities of crystallization of polymer because we have long chain and so on. So in fact, it is limited to describe nucleation of isothermal data and close to the melting temperature, because this equation does not account for the fusion effect that occur when you are close to the glass transition. And diffusion is very important at low temperature. So now, if you look to the Hofmann-Norrissen theory, you see that you have this equation, two exponential terms, the product of two exponential terms. So one term is related to nucleation, when you crystallize from the melt, and one term is related to diffusion, when you crystallize in the glass region. And you see that the product of these two terms will give a bell-shaped curve. So it means that the crystallization rate passes through a maximum. It is very interesting because in that case, we have a very good link between the theoretical aspect and the industrial application. I will not go into detail, but you all know that here the size of the crystal are different and the properties of the polymer are different. And here you have bigger crystals, but not the same properties. And it also corresponds to industrial process from extrusion. And when you make here in this region, you make the stretch blow of, for instance, bottle blowing. So this is very interesting also. We have developed a new method to determine the Hofmann-Noritsen parameters U star and Kg. So to develop this method, we have applied what we call the isoconversional derivation to Hofmann-Noritsen equation. So we just apply this derivation. I do not go into detail. It takes some time to do this, but we arrive to this equation. If you look to this equation, what do you see? You see that if you have the variation of apparent activation energy with temperature, by a nonlinear fit, you can estimate U star and Kg. And this activation energy dependency is simply obtained by simple DSC measurement. So it means that by simple DSC measurement, you can determine U star and Kg. And the classical method was limited to isothermal data, and only Kg was determined in this method, and U star was set as a universal value. Generally, it is done by microscopic measurement, and it's much more difficult to do. So we have this new method, and I will show you that it is a very convenient method. So first example concerns a new bio-based polyester, which is called PHF, and which was the work was done in collaboration with our Greek colleagues, Professor Papageorgiou and Professor Bikaris, that make the synthesis of this new bio-based polymer. So then what we have done, classical DSC measurement, we have studied crystallization on heating and crystallization on cooling. And we also have changed the set of cooling rate used in order to see if we have a change in the crystallization mechanism according to the temperature domain where the crystallization occurs. So this is what we obtain for this apparent activation energy variation. So you see here that we have a variation. So first conclusion, it is not a constant. So it is a multi-step process, and we must not apply single-step equation. The value here corresponds to the mean value of the cooling rate used. Then, if you change the cooling rate, you see here, you increase the cooling rate, you see a shift of this apparent value, and you reach quite the value 0 here at the end. So you see that we have change according to the temperature range of crystallization. So we have a change in the crystallization regime. And also I will show you that each time we have a break in this activation energy dependence, generally it may attribute it to a change in the crystallization regime. So the conclusion is that we have different mechanisms according to the range of cooling rate used, and we can also identify change in the crystallization regime. We did the same for heating, so crystallization from the glass. The conclusion is similar. We have a complex process, a multi-step process, and we also identify some change in the crystallization regime. So now if we plot this variation as a function of relative extent of crystallization here, this is what we obtain. If you look to the crystallization from the glass in blue, you see that we have positive decreasing value. And then if you look to crystallization from the melt, you see that we have negative increasing value. So I agree, negative value of activation energy, it is something strange. And the first time we obtained that, we had a lot of questions about that. So the question is there a physical meaning of this value? So we have to understand that in this case, the apparent activation energy is not an energy barrier. It just represents the temperature coefficient of the Arrhenius rate constant, because we use an Arrhenius equation. So because the process is anti-Arrhenian, we simply observe negative value. So it is not an energy barrier. Then why do I believe that this value have a physical meaning? Because we observe a general shape of this variation. So you can see here that for many different polymers and different teams in the world have obtained exactly the same general variation of activation energy. I mean, for the melt, increasing negative value, and for the glass, decreasing positive value. And finally, we have found an explanation. In fact, each time you have this negative apparent value, it means that the process is controlled by nucleation. So that's why we have observed this for crystallization on cooling, but also for gelation on cooling, for solid-solid transition on cooling, and for polymerization with formation of a liquid crystalline phase. Maybe you know that in my team we have studied PEF, polyethylene furan dicarboxylate. We were one of the first team to study this new bio-based polymer, which is supposed to replace PET. So we did this in European project in collaboration with Avancium. And if you look to this graph, you see that we obtain exactly the same tendency for PEF, different value, but always the same tendency. So this is a proof of the physical meaning of this strange value that we get. And initially, the first study we did, it was a long time ago, here, and it was on PET. And if you look to PET, you see that we also observe the same trend. And you see here, we have a break in this variation that I will comment later. So now if we come back to PEF, I can plot the activation energy versus temperature, and by the nonlinear fit, I can estimate quite easily the Hofmann-Lorentz parameters U star and Kg. And then what I look is there is a change here in comparison to what is predicted by Hofmann-Lorentz theory. We have a break at this temperature, 170 degrees. And we publish this, and we propose that there is a change in the crystallization mechanism at that temperature, only by looking at this graph. And this was confirmed later by different authors that make much more sophisticated measurements with SACs and WACs. So this is a proof of the validity of our simple computations. And now if we come back to PET, at that time we have observed a change, a break here at 200 degrees. And by looking in the literature, in fact, it was known that there is a change in the crystallization regime at this temperature. So you see, you can get some mechanistic information thanks to this method. So now I come back to PHF, and I can make the nonlinear fit and estimate the value of U star and Kg. And then I can compare this to Hofmann-Lorentz theory. So I have proposed a new method here to estimate the temperature at maximum grow rate. So in fact, once you have determined U star and Kg, you can plot this curve. So you cannot estimate G0 with DSC. So you just plot the product of these two exponential. And normally, this must correspond to the temperature at maximum of grow rate. And now, if we want to go more into detail with the explanation, you can look to this part. So if you look to this part of the curve, what do you observe? What is predicted by Hofmann-Lorentz theory? You see that when the temperature decreases, the grow rate increases. So it means that crystallization from the melt is an anti-Arrhenian process, and that's why we observe negative value of this temperature coefficient. And now, if you look to the glass part, you see that when the temperature increases, the grow rate increases. So that's why you obtain positive decreasing value. And because to go to positive from negative value, you must pass by 0. And that's why you have this value of 0 that corresponds to the maximum of the grow rate. So by using this new method, I have estimated the value of the temperature at maximum grow rate at about around 80 degrees. But the question was, this is a computation, so is this computation correct? So to check this, I have used the fast scanning calorimetry. The fast scanning calorimetry is a very convenient tool because you can heat the sample and cool the sample very, very fast. So you see here the heating rate. It's not a mistake. It is Kelvin per second. So by cooling the sample very fast, you are sure that there is no modification of the structure. So to perform isothermal measurement, for instance, you start from the melt, you cool very fast to the isothermal temperature, and you are sure that the sample will not modify and will not crystallize. So this is a very convenient technique. And so we have done this. We have performed isothermal measurement with the fast scanning calorimetry, and we have determined the time at peak maximum temperature. And you see the value that I got at 84 degrees, which is quite close to the value that I predicted with my method. And then an interesting conclusion is that more accurate fit is obtained by using TG minus 50 degrees for flexible polymers such as PHF instead of the usual value of minus 30 degrees. So I don't want to go into detail with the explanation of the computation, but just I want to say that it is not just a simple fit of the data. There is many methods where you just fit the curve with this very complex equation and you get these parameters. The problem is that in that case, parameters will not have a meaning. So what I am doing is it's much more difficult, take more time. So I start by fitting the activation energy dependency. I obtain U star and kg. Then I kept U star and kg constant and I try to estimate equilibrium melting temperature and so on and so on. Step by step, finally I fit the crystallization rate curve, and each time I fit 1 or 2 parameters maximum, but not fitting all the data to avoid overfitting. Then I have proposed a new method by combining the Hofmann-Nouritzen equation here and this equation that corresponds to the reaction model, crystallization model. So as you can see, I do not use the Arrhenius rate constant because with Hofmann-Nouritzen equation, I have a term that take into account diffusion and a term that take into account nucleation. So it is much more efficient to modelize the crystallization from the glass and from the melt. So this method was implemented in the Netsch software, as you can see here. And they apply this for industrial problem and say that they have very good results. And it can describe crystallization over a wide temperature range because we take into account the diffusion. They do not proceed step by step, but so it is slightly different, but they say that it works very well. So once we have estimate the crystallization parameter, we can make several simulations for various conditions. So as you can see here, or to fix an extent of crystallization and see the time according to the temperature we want. And why it is also very important, because now we also all study recycling of polymer. And what we noticed is that the crystallization rate of recycled polymer is very different. So there is a lot of interest to study this mechanism. So second application is about thermosetting polymers. So again, the idea is to show that we can obtain new insight in cross-linking mechanism, make some modelization and simulation. And also I have developed specific method to follow polymerization in viscous media or in the solid state using rheological or DMA data as you can see here. So the example show you concern bio-based thermosetting polymers. We have developed new eutectic hardeners to cross-link epoxidized vegetable oils with natural diacid. So why we use natural diacid? Because they are non-toxic, and the idea is to replace toxic amines that were used in the past. And epoxidized linseed oil are also very interested because they are non-toxic, so we can obtain fully bio-based, non-toxic thermoset. The problem with this natural diacid is that they are solids. So this is the oil that you probably know. You know the soybean oil, castor oil, and we use the linseed oil. So in fact, what we use is the epoxidized linseed oil, which is called ELO. It is interesting because it is bio-based, non-toxic, and commercially available. And then we made this eutectic hardener. To make this eutectic, we have used what we call liquefiers. So this liquefier are diethyl succinate, diethyl malonate, triethyl citrate, diethyl oxalate, and diethyl glutarate. And we mix this liquefier with citric acid, a natural diacid that normally is solid. So this is how we proceed. We mix the sample, we heat, and we have an homogeneous liquid. And we plot the phase diagram. And if you look to this phase diagram, you will see that we can decrease the melting temperature of citric acid. So this is very interesting to prepare homogeneous sample. And another interesting point is that by making this eutectic hardener, we highly decrease the viscosity. And the viscosity is very important for application. So you can see here that we can obtain very low viscosity, which are very interesting for industrial application. Among all these systems, we have studied the reactivity. We wanted to compare and to understand why the reactivity was different for all these systems. And initially, you see the one which is called TEC has a higher viscosity. So we were thinking that the difference in reactivity arises from this highest viscosity, but I will show you that it is not so simple. So this is the way we prepare the homogeneous polymeric mixture by mixing the ELO with the different eutectic hardener, and this is the optimum ratio. We have optimized the ratio. So now we can apply the kinetic analysis, and this is the reaction rate that we obtain by DEC. So you see that the curve are very similar for all the eutectic, except the TEC one that start at a lower temperature and end at a slightly higher temperature. Now, if I compute the activation energy, this is the dependency that I obtain. So again, we have a complex process. But what we see is that these three follow a similar trend. I mean that the activation energy decreases. And for KTEC, we have something completely different. We have an increasing value. So decreasing activation energy generally is associated to an autocatalytic reaction. And so for KTEC, you see that it cannot be autocatalysis, and that's why I postulated that we have, in that case, two competing reactions. And now we can compare this value with the reference system. The reference system is done with ELO, citric acid, but without liquefier. And what we see that the use of the liquefier highly decreases the reaction temperature. So this is very interesting because with the liquefier, we decrease the viscosity and we decrease the reaction temperature. And for industrial application, these two parameters are very, very important. Now, if we look to the activation energy dependency, we see that it is very different without a liquefier. We have a strong decrease of activation energy at the beginning that corresponds to autocatalysis, and we have shown that the low value at the end generally correspond to a control by diffusion of short polymer segment. So we wanted to find an explanation of the difference in reactivity, for instance, between one of the systems, DEM, and the tech one, which is very different. So we made rheological measurement. We look at the TJ, temperature at gel point, and we have similar value. So this is not an explanation. Then we look to the viscosity, and we determine the minimum of viscosity. So there is a big difference between the reference system and the system with eutectic hardeners. And if we come back to viscosity, so for Catech, viscosity was much higher without ELO. So we are thinking that this explains difference in reactivity. But now we see that when we add the ELO, the viscosity, in fact, are very similar. So difference in reactivity cannot be explained by viscosity. So now I have computed the mathematical function that describes the reaction mechanism. And what you see here is that for DEM, DES, and DEG, there is a similar trend. So I will not go into detail. Then if we look to Catech, again, we see a big difference. So I'm not saying that all the polymerization mechanism is here because it's much more complex, but we clearly see some difference. And for the reference system, again, we have different mechanisms so that we attributed, for instance, here to diffusion control. So it is in agreement with diffusion control. And then I wanted to modelize this polymerization rate. And we have proposed a new equation recently that was published in this journal that perfectly describe polymerization taking into account autocatalysis and diffusion. So to do this, I will not recall, I proceed by step by step. It's not simple fitting of the data. So several steps to obtain these kinetic parameters. And then, if we focus only on this value, you see that for Catech, the autocatalytic exponent is close to 0. So this confirms what we learned from the activation energy dependency is that for this system, there is no autocatalysis. So this is not the right mechanism. It is something different. And then if we look to the other system, it is in agreement with autocatalysis because we have the activation energy of the non-catalyzed reaction, which is higher. And also we have value that agree with diffusion of short segment when the polymer is cross-linked. So when you have a solid, diffusion of a short polymer segment is very important. So then you see that application of this method make it possible to have very good fit of the data. But again, I recall it is not just simple fitting. I think that the value that I have obtained have a real physical meaning. Now for Catech, I have proposed a different model, two-step computing reaction. So the computation were the same methodology. And you see that applying this kinetic scheme, it is possible, again, to obtain a good fit of the data, but with value that have a physical meaning. And now, another interesting point is that with the model-free method, we can estimate the contribution of the pre-exponential factor and the contribution of the energy barrier. So we can separate these two contributions. So if we look to the reference system and the DEM, you see that the contribution of exponential factor decreases and contribution of exponential term, energy barrier, increases during the polymerization. So this one decreases and this one increases during the polymerization. And again, if we compare with Catech, we see that it is completely different. So it is the opposite. So in fact, this term increases, the pre-exponential term increases, while the energetic barrier decreases. So again, a different reaction mechanism. So the different reactivity of Catech is in fact explained by a more hindered structure of this molecule. In fact, for this system, the reactivity is driven by increase of pre-exponential factor, and the computation show that this value increase during the polymerization, while it decrease for the other system. And the most limiting term is not the energy barrier, but the efficiency of collision. So because we have this triethyl citrate that have an OH group, in fact, we have less cross-link because this OH group can react with carboxylic acid group. And we also have less efficient collision because the structure is more in the red with tech as compared with the other. And the increase of activation energy is in agreement with two competing steps, where we have reactivation of chemical reaction at the end because we have unreacted monomers with this structure because the molecule is more in the red. And now the relation with phenol properties. If we look to phenol properties, if we look to the glass transition temperature, we see that the highest value is for the CADEM and the lowest value is for the kinetic. And you see that we can make a correlation between the mechanism and the phenol properties. Again, if we look to Young modulus and tensile strength, again, CADEM has the highest and kinetic has the lowest. And it is the same if we look to quite all the mechanical values, always CADEM the highest and kinetic the lowest. And now, because we are involved in a European project, so in this project we started with vegetable oils, but because they want to develop application for aerospace, boat, and automotive, so initially when they wrote the project, they were thinking to work with vegetable oil, but the glass transition temperature are very low. And I say to them that I didn't really believe that it was good for aerospace application, but they didn't really listen to me. So the mechanical properties are very low. So we moved to a more rigid structure. So we have used a more rigid bio-based epoxy monomer. It will be published soon, so I did not disclose. In complement with the formulation that we have, the ELO and the eutectic hardener. And you see that in this case, we can reach high glass transition temperature from 80 to more than 100 degrees. So I hope I will not be too long. So thank you again. And as I told you, I am open for collaboration. So don't be afraid by theoretical and computational aspects. We can make this in collaboration. Thank you very much.
So thank you very much for that very interesting talk. Now the floor is open for questions. If no one else has any questions, maybe I'll take the liberty of asking one. So this is very interesting that you're able to predict the properties and the crystallization and the energy involved. Have you ever perhaps looked at the biological aspects of these and whether you could predict? Because crystallization is also very crucial for bioactivity of polymers. So we see, for example, a more crystalline polymer has a higher or a lower degradation rate, and that then changes the tissue engineering kind of thing. But I don't know if you have looked at that at all.
Okay. Yes, I agree. Crystallization degree will be very important. We did not do that for this polymer because it is not the goal of for boat and space, aerospace. But I agree with your comment because we have developed a new gel for tissue engineering, wound healing. I am not a specialist. I am not able to look to biological data, but we have developed a new gel. Now it is patented. And we work with a biologist that made this test. And we have very interesting results. And I agree with you because what she noticed is that the size of the pore, the size of the pore, the degree of crosslink, because the gel, it is a chemical gel, so we also have a crosslink, is very important for cell growth and cell adhesion. And the interesting point is that in my team, we are able to tune the property of the gel, because generally people that made gel, they just made one gel and it's okay when it's done. But because we have all this rheological measurement, we can do this. It was very good in complementarity with the biologist. And for sure, there is something to see between the degree of cross-linking, the size of the pore, and the activity. And to end with this gel, now it is patented, and we are looking for industry which would be interested. Maybe you know a lot. Because according to the biologists, the properties are very interesting. And what we have done, we have mimicked a process that is done by an alga.
I see.
In fact, in the Mediterranean Sea, we have an alga. And when you break this alga, she produces a gel.
Right.
And that's the way she protects and she repairs.
I see.
But the link between, crystallinity degree, degree of crosslink, size of the pore, yes, I'm not an expert in biology, but from what I have seen, and this colleague told us that it's very interesting for the cell growth, cell adhesion. But you know more than me.
No, not at all. I'm sure you know much more. One little add-on there is you've mainly looked at pure polymers from your examples. Would you be able to predict similar things with blends at all?
Yeah. For me, it's not a problem because it's macroscopic data. It's not so pure. What I noticed, because in the past I was working on a petrol-based polymer, and I can say that the curve, they were much more nice with.
I see.
And what we see is that with natural polymer, it's much complex. So maybe they are not so pure, and I don't exactly know what is the difference, but the mechanisms are much complex. And if you look to the DSA data, if you look to some part, you see that the fit is not correct, but I am sure that it is not my method. It is because of the data.
I see.
Because you see that it's not regular. In the past, I was working with Jeba. With Jeba, I can show you some fit. It is like if you draw it by hand. It's very perfect. And I never obtained that with bio-based polymer, even for crystallization and for polymerization. So I think there is something which is very different with natural polymer. It's much more complex.
Right. Thank you very much. Can we take another question?
Yes, of course. Yes, we have time.
Please. I think the mic's arriving.
Talking about the activation energies from the glass and from the crystallization for PEF and PET. You showed the data, on the epsilon axis quite quickly, so maybe I'm saying something wrong, but maybe the data were not overlapping, but very, very close. Is this my impression, or this is my first question? Second question, I'm not much expert in PEF. I'm learning a bit about PET. PET is often considered a polymer. In reality, it is a copolymer because it contains also some co-units arising from polymerization. And this affects a lot crystallization. There are a number of grades depending on the catalyst system, on this little monomer content. Maybe, the large research efforts on PEF are devoted to substitute PET. Maybe there are some grades of PET that can be more easily substituted by PEF. Yep.
Yeah, but we also have to mention that PET, we bought it.
Okay.
So it was quite pure.
So you don't know what kind of grade and the exact composition?
Yeah, I have only the data that were given at the time. It was by Aldrich, but we didn't look at the purity. I noticed this morning one person mentioned about the purity, and I didn't know that. So, but now for PET, we bought it from Aldrich. Yes, I agree. If you look to this value, they are quite similar.
Okay.
It
Especially from the core crystallization.
Yeah, it means that the crystallization is not so different.
Yeah.
But after that, we can compare the value. We go to much lower value for PET, and this corresponds to the fact generally if the crystallization is close to the melting or less close to the melting. If it is closer, we will have much higher value. For instance, we did it on PTFA, polytetrafluoroethylene. Crystallization is very fast, so you obtain very, very low negative value. But also one point here about PEF. Because this study, it was done in 2040. And in fact, it's PEF from Avancium. And at that time, the synthesis was not optimized. And I didn't put the DSC graph, but if you look to the DSC, it's not as nice as PET. At the end, you have some... Yeah, some crystallization is not really finished. So I think that since that time it was optimized. But as I told you, I think that we have a big difference between natural polymers and bio-based. Because if I look to the crystallization curve of PET, they are very nice, but not the one of PF.
Okay, thank you.
Thank you. I think there was one more question. At the back, yes.
Yes, thank you very much for the very interesting presentation. I really like the part on the liquid hardeners. I was wondering, what's the fate of the ester that you put inside your reactive system? Because you start with acids, you have epoxies, you have a lot of hydroxides later, you have a bit of an ester. Is it part of the structure of the polymer, or is it plasticizing something? From
the NMR, what we look from the NMR is that normally there is no reaction with the other, except it for one DUS, I guess, if I remember well, where we identify some small interaction. But globally, it's much more like a plasticizer. Okay. But the point is that it destroys hydrogen bonding of the citric acid, and that's why we decrease the melting temperature. And the point very interesting is that we can have, because the industry we are working on was very interested by room temperature curing, so we can have very low temperature curing and very low viscosities.
Okay.
Okay, thank you.
And it was developed for industrial applications.
Thank you. I guess if there are no more questions, thank you very much for that amazing talk.
Thank you.